So I'm Beau Paisley with ARM. I support our debugging and performance tools. I wanted to highlight the cross-performance thing. We were a small company that was purchased by ARM quite a few years back, but we're still entirely committed to cross-platform support. So we support ARM, x86, we still support Power, NVIDIA, and we're just working on support for ROCm also. So I just kind of want to go over the agenda a little bit. I'm going to give a very short slide presentation just to give the high-level overview of what our tools are. And then during this session, do an interactive demo of just some of the highlight features. There's more that can be covered in this session. So in the breakout, how we use that time is up to you. If you want to see some things in more depth, I can spend some time with that. If you have a bug that you can get set up on Theta, if you have a bug that's outstanding, I highly encourage you get prepared to work on that during the breakouts. We and TotalView will be there, and the Argonne experts will be there, and I bet between all of us we can help you find a solution to your bug. So if you have a bug on Theta, I suggest you to get set up on that. Also in terms of performance tools, sometimes getting set up with performance stuff takes a little bit longer. John and Samir will be speaking this afternoon, and they both are experts on a couple outstanding in-depth performance tools. And I believe they are going to be here for a couple sessions this afternoon. So on performance also, I highly encourage you to get set up with one of the tools after you've seen things, and there's a couple more sessions where you can take advantage of. Sometimes getting that data takes a little time, so I just like to mention it early. Figure out how to get that data, hopefully by dinner, so after dinner, or maybe even beforehand, one of us can help you out on one of those type of issues. So ARM Forge. So Forge is the integration of our debugger DDT, our application profiler performance reports, and our source code profiler map. It's designed from the ground up to be highly scalable, both in terms of architecture and user interface, very focused on traditional HPC, and by that I typically mean SPMD type of computation where you're using MPI and OpenMP in a domain decomposition type of architecture. Very focused on that. Ease of use obviously is important. Now I'm just going to give a couple highlights of features that I think are very uniquely focused on HPC. We've talked about printf, and that's only half a joke of, like with a lot of new customers, printf is still the debugging tool of choice. And not a problem with that, but in HPC particularly, as you move to larger scale with more data, more determinism, that's very difficult. GDB is a first step out, but as you move to larger scale with many processes, using some of the tools that you're going to see today will really ease your life. And in terms of DDT, this is just some of the highlights. Scalable print, this is the ability to print values across thousands, tens of thousands of processes and tell what's going on, which is pretty onerous if you're already doing it with print statements. Watch points, the ability to halt execution dependent upon the value of expression. So especially in large codes, HPC codes where there are a lot of people involved, trapping dependent upon an expression is very, very helpful. Static analysis, the ability to find problems before you even run the code in earnest. So things like using uninitialized memory, failing to free memory, variables that not have been initialized, that type of thing that can be caught statically. Memory debugging, the ability to read or write, detect if you've read or written outside of an array, heap corruption, just being able to track memory, so if you're leaking memory, that type of issue. So that's just a highlight of some of the DDT features I think are important. Performance, moving into performance, and before I talk about the tools, I just want to talk about a little bit about methodology. For both HPC debugging and performance, methodology is really important. I gave a talk at GTC recently on debugging methodology, and I'll have that in the end notes. Approach debugging systematically. Performance, it's equally important, perhaps more so, is to follow a system. And this is a nice little fun chart the marketing guys did for me of kind of the roadmap to follow. And in performance, there can be orders of magnitude difference in problems. For example, the performance you lose by not getting complete vectorization might be a couple factors, a few factors, whereas if you have I/O messed up, you might be missing out on orders of magnitude in performance problems. MPI communication also can be orders of magnitude. So the point is if you're tackling performance, kind of move through this roadmap in order of the problems. Number one always is correctness. Do your regression tests before you run, whatever you have set up for that. There's no reason in optimizing if it's not correct. We can all make it super fast if it doesn't need to be correct. So every time you're iterating through continual regression tests, start with I/O, and move along through each step. And I won't go through a lot of them in detail, but the point is think about the large operations that can cost the most and start with those. So in terms of our tools, performance reports, this is a one-page output. So at a very high level, you can see what's going on. So things like if there is an imbalance of MPI, it stands out very quickly. You do not need symbols for this, so very easy to get on your release build. No instrumentation, very high level, extremely low overhead. Quick snapshot for like that first step on the performance roadmap to give some more detail of where to focus. So MAP is our source code profiler. This is a sampling-based profiler. It does not require any instrumentation. Also, it's very scalable in that it uses sampling technique where it samples at a given frequency and then in time resamples the data onto a new time base and decreases the sampling frequency. So you can run very long programs. Unlike some other tools, our focus is run your full HPC job at scale at its full natural phase, and it gives you very kind of high fidelity at those type of scales. Once again, just some kind of peak features that I think, or important features that I think stand out in MAP. It's very visual, so being able to see peak memory usage, MPI imbalance. Once again, thinking about the performance roadmap, look for I/O and MPI issues first, then move on to memory and CPU-related operations. MPI, being able to see vectorization issues. So Python profiling, so I'm not going to really get into this much today. It's relatively new in our tools in both debugging and profiling with Python. We're seeing an enormous uptick in a lot of sites. One I like to quote is NERSC. In the few years I've been working with them on Python, they've gone from about 10% of their user base to 75% of their user base are doing Python HPC. So I don't mean data munging, I mean stuff like using MPI for Pi, real HPC, especially among early career scientists, seeing a lot of new projects that are getting born in Python. So exciting technology, very productive as Python always is. Just a little bit of follow-up materials. So very important is how our tools work here at Argonne, the links for a setup for that. A set of videos, very short videos of just a few minutes of how to do memory debugging, how to look for I/O problems, that type of thing. Some broader, what ARM is doing in HPC, some Python, then an in-depth presentation. So for the student cluster competition last year at SC, I did about an hour and a half presentation on our tools, which doesn't cover everything, but it goes into much more depth than we'll probably cover today. And recent thing I did at GTC on using methodology in debugging. So I'm going to move on. I want to do a little bit of hands-on stuff, and like I said, I'm just going to touch on high-level aspects of it. So a couple things I wanted to mention on performance. I think it was Kevin mentioned earlier today, a lot of these tools are converging, and you're going to see a couple really high-power tools this afternoon for doing really in-depth performance analysis. That is definitely true to an extent of these are all mature tools, and at the time we kind of evolved to cover the same bases. On the other hand, I think there's still a lot of areas where all the tools out there provide unique strengths. Our tools, I kind of think the unique strength is ease of use for more of a domain scientist end user. We really focus on, especially with large sites, trying to make it usable by an end scientist who might not have much or any expertise in performance tools or sophisticated debuggers or anything. Try to get it in their hands so they can solve some of their own problems, or at least find the location of the problem and escalate that to an expert that can help them. So I just kind of like to highlight that, and I think our focus is a little different than some of the focus of other tools you'll see today. So I'm just going to run the demo in my virtual machine here interactively. The real workflow for our tools is you install a client on your desktop, and we have clients for Linux, Windows, and Macintosh. And from the client, you connect to your cluster, and it does an SSH tunnel into the cluster. For Argonne, that's all described on the web pages that I referenced in the endnotes. And we'll go through that some also in the breakout session of actually setting up or connecting with a client and submitting a job. Then you log into the cluster and you modify your batch script to launch the job from the batch script. When it launches, it'll bring up the client and you start from there. Just because it's a lot more efficient and expeditious, I'm just going to run from my machine here. So starting with a simple DDT example, and this is a kind of a toy C++ code just to walk through some things. And of course, it's slower in demo mode. Okay, so let me go through the user interface a little bit. There's operations for running processes, manipulating the stack frame, disassembly mode. So this is relatively new. When we first started looking at this several years back, it was like, boy, hardly anyone does that. Personal opinion is that's actually becoming more important as we're looking at a lot of different architectures. For better or worse, being able to look at disassembly mode in a little more detail is becoming more important. Icons for manipulating the processes that you're looking at. So in this case, I'm looking at the context for process 0 out of 4. On the left-hand side, kind of a navigator, kind of like an IDE you might see in Visual Studio or some of the Eclipse tools. To the right, the source code view. As I mentioned, the static analysis of those roadside warning-looking signs. If you hover over them, they'll give some information about some potential problems. Also within the source code view, you can edit, rebuild, and redispatch. So it's not intended to be an IDE, but for cases where it takes a little while to get your turn on the system, and you have a scenario of like, boy, I can make this quick fix, recompile, and think that I'll fix the problem. It's kind of a quick hack to do that. So you can just edit, it'll dispatch new executables to the compute nodes without having to go through the batch system. So don't treat it as an IDE because for one, you'll be hogging up the system sometimes in that type of mode, but a way to do kind of quick fixes. So let's step along a few lines here and instantiate some stuff. Okay, on the right-hand side, different views on variables. So the current view is to look at current lines, which in old school Fortran, which is what there was when we started, there would be a lot of stuff in scope. More typically, you can go to the locals tab and get everything that's in local scope. And if you hover over variables within this, it'll give you some information about the type. If it's been instantiated, it'll give you some information about the values. For structures, you can drill down to elements of the structures. You can also drill into elements of arrays, but a little later we'll look at a little more visual way to look at arrays. Then to the right of the variable, it has a little plot, a sparkline plot, which shows the value of the variable across all of the processes. And you can click on that little glyph and say, view across processes and get the actual values, some statistics of the values across processes. You can export it to CSV or HDF files, do some post-processing, those type of operations. So this is a very powerful tool in terms of the scalability of being able to see that the variable has the a priori value that you expect. So for example, my rank is typically going to be this monotonically increasing straight line. And if it's not, you might have a problem. And folks always ask of like, well, you only have 1632 pixels there. We actually do some kind of statistic subsampling. So if you're running 32,000 ranks and there's one rank that's messed up, it's going to still stand out. So it's not it's intended as a first diagnostic of are things as you expect, or is there something standing out that merits a little more investigation. Okay, breakpoints. Let's start with breakpoints. So breakpoints are the ability to halt execution at a specific location conditionally. So I recommend, especially when you're getting started, there's a lot of accelerators in DD, but when you're getting started, use the menu. So go to the tab of interest, right-click within the body of the tab, and bring up the dialog. The dialogues are pretty self-documenting, and using these, the tool overall is relatively simple to use and self-documenting. So a lot of flexibility in setting the breakpoint. You can set it for a specific process group. So for example, if you know the process is limited to a subset of processes, or if you're in a coupled model type of run where you're only interested in part of the model, it's a way to focus your search in that way. You can also limit the domain of the search. And probably one of the most powerful is set it conditionally. So a very common case we'll see is that a problem doesn't occur until after I, J, K, iterator, whatever. We'll specify in as much as you can. One thing we do in in-depth training is really focus on methodology. And one of the most important methodology aspects debugging is give some thought in advance. I like to talk about like using the scientific method of making your hypotheses of what the problem is, and then set a domain for your search. And this has two components of value. Is one, your thought process and what the problem is behind the hypotheses. You're probably going to be more fruitful. It is a lot less data to go through. So whether you're printing out values from the debugger or print line or whatever, the more you can focus your search into the known problem space, the less you're going to have to sort through, and of course, less overhead on the debuggers. So really encourage giving some methodology debugging. I find it's a unique area in that it's very easy to say, boy, I really think I know what that problem is. I'm going to dive in and I'm going to have it in 5 minutes. And the number of those 5 minutes that turn into days is enormous. I mean, no one sits down at a MATLAB script and says, oh, this is going to take 5 minutes, it takes days. Debugging is unique in that the magnitude of the problem is hard to judge. So approach every session systematically. And lots of them will be 5 minutes, and that's great. But when they're not, and they're very difficult, it'll pay dividends. Okay, so I selected run, the little arrow there, old VCR style. And it paused all 4 processes on line 122. So this blue line kind of gives us some indication of where we're located. If you hover over the blue line, it will show which processes are located there. In my fairly simple program, all 4 of them are there. In larger runs, as things diverge, so that's a really powerful tool to see which processes are located at a given line in different locations. Okay, so breakpoints. So let's move on to trace points, which I mentioned in the overview. And we've all made fun of print statements, so this is our answer to print statements, is being able to output values from the debugger without having to rebuild the program, and more importantly is changing the determinism. Is when you put in print statements, even in simple programs, you're changing the determinism, and depending on the nature of the bug, typically if it's a memory-related problem or the bounds error, those type of things, it is super common, even with a serial program. And as you move to larger scale, that type of determinism grows exponentially. Worked with clients where it is pretty much a guarantee. In fact, there's been cases where folks are like, if I take the print statement out, it prints out null, it doesn't run anymore. Obviously, that's not a great solution. So trace points, it's a way to output values within the debugger. Once again, go to the tab, use the dialog. It's kind of self-documenting. We can halt by line location or a function entry point for a specific process group. So once again, very similar to the breakpoints flexibility. We can limit the domain. This is an iterator. This is just going through an iterator space. I just want to get a high-level view, so I'm going to say, how about every other pass? Unconditionally in this case, but once again, that's one of the more common ones. If you can focus the IJK iterators within some bounded domain, you're really going to probably isolate the location. Okay, so let's run all of the processes past that block. So I'm going to say run all processes to that statement.
While you're waiting for this, just to be clear, the trace points don't actually fix the non-determinism problem with printf. I mean, you're putting in your own Heisen timing.
So timing-wise, that problem does not fix. The problem that's related is when you put in a print statement and you're moving stuff around in memory and you have a memory-related debug, it definitely eliminates that. In terms of timing, you're reducing it, and the cost of the timing of what we do is relatively low to a printf type statement in C or Fortran. But no, it doesn't eliminate it. I think it'll minimize it, it moves it. Okay, it's on the AV cable, so it ran slower. So let's go to the trace point output. So outputs the value somewhat like we would from a print statement, but a little more scalable, so it shows the explicit range. It uses the sparkline plot similar to what we have in the local tab, so you can get a feel for the shape of the variable across the processes. All right. So we saw in the locals tab how to look at atomic data, structured data. You can even look at arrays there. An alternative way for array type data is use the array viewer. So click on the token. So another usability tip in DDT is whenever you click on a token, it'll bring up a context menu that's often kind of self-documenting of what makes sense that you can do in that context and bypass the documentation. So in this case, I want to bring it up in what we call the array viewer. So right-click on the token tables, select View Array. So it picked up that this was a two-dimensional 12 by 12 array. By default, I'm going to have a look at it in kind of spreadsheet form there. And we can subsample this. Oops, there we go. So kind of isolate into the indices. So particularly useful for finding the indices of things like nans and infinities. So you can put in not is nan, not is inf. Really powerful way of finding the specific indices where those type of things occur. We can also bring it up as a picture. So especially for larger data sets, a nice way to see that it has the shape that we expect. So a lot of discussion today on GPUs. So we support GPUs. We support NVIDIA for ages. We are starting support for ROCm at Oak Ridge. I always think of them at this point, because this feature I think is particularly useful on GPUs where there's a lot of mistakes that can happen in the pipeline of stage your data on the host, get the data to the GPU, do the work on the GPU, move the data back to the host and verify it's correct. So a lot more steps than if you were doing it on the host. And this is a great tool for seeing that each of those steps are correct. So get it on the GPU and bring up the data visualizer. It is what I expect, is what I expect. Okay, so we saw in the locals tab how we can view values. So we can actually edit values also. So if you bring a value down to this evaluate window, once again, right-click on it, and it will give you a lot of the options of what you can change. So a lot of ways you can manipulate it. For example, play with the pointer casting. So especially in C, C++ applications where you want to play with the casting to see how it will affect it. Changing the actual type, or actually editing the value. Let's do something dramatic. So we see that Sparkline updates to show that outstanding process. So once again, this is a place I like to kind of bring up methodology again. This is a powerful way to do diagnosis, but when you're doing this, give some thought to your hypotheses of like, if I change this value from X to Y, it will have the following outcome Y. And if it doesn't, then log your reasoning so when you come back to it. And you can actually like keep your logbook, your scientific logbook within the application. The logbook keeps track of your history and you can make kind of notes of your hypotheses. But I'm still liking my notepad type approach too. But the important part is it's so easy to be haphazard when you're debugging, because at every step of the way, even when a 5-minute problem is turned into an hour, it's just so easy to have the inclination of like, oh, I know what it is, I'm going to try one more thing. But start from the beginning with a little bit more process in mind, and overall, you're going to be a little more fruitful about it. Okay, so breakpoints, halting execution at a location. Trace points, outputting values. Watch points, halting execution dependent upon the value of the expression. So for cases where you get to a certain location in the code and the state is not as you expect and you have no idea where upstream the state changed from what you expected, watch points might be the approach. So somewhat similar to breakpoints, once again, we can focus on a given process or process group. Enter expression, I'm just going to enter a defined variable that's in scope in this context. And we can halt on read or write or both. I am going to halt on both. And select play. Okay, and it halts at line 148. So the first statement after being watched is assigned a new value and shows us the old value and the new value. So one other thing I want to show in here before I move out of this sample is just to reference memory debugging. Memory debugging is a fairly deep topic. I'm not going to go into any examples here. We can go into it in breakout session if you're interested in learning more about that. The two main things for memory debugging is memory stats, memory usage. I didn't turn it on for this run, so they're not available. So let me actually restart. I think we have time for that. So while this is getting started, let me just talk about this. It'll take a moment to get running again, is offline debugging. And I'll probably have a chance to show you an offline output, but I just wanted to talk a little bit, and I have some references in the endnotes of my slides. Offline debugging is the ability to run the debugger without the user interface. So you set up breakpoints, watch points, trace points, all the features that we've looked at. You define those. You submit your job as normal. It does not bring up the user interface. Instead, it generates an output file. You can either have it as CSV or HTML, and then study the file afterwards. So particularly important for large-scale runs. I would say without exception, the most success stories we have of large-scale bugs being found, it is within offline mode. We've had several at large systems where like full scale of the machine had to be accepted. Bugs that were outstanding, offline mode was the tool of choice to find those. So cases where it's large scale, it takes a long time to get your turn in the queue. Non-determinism, if it's a case where you might have to run for hours sometimes, for minutes with others, offline mode is a great way to go about it. And I'll show you an output if we have time for that, but I encourage you to have a look at the end notes from the slides. Oh. Trying to think, talk, and do at the same time never pays dividends for me. Forgot to turn it on. So you have to turn it on. By default, memory debugging is not turned on. There's a bunch of sub options for optimizing the performance of it. I kind of had it set to some defaults that work pretty well on average for minimum overhead. So the main tools for memory debugging are memory stats and memory usage. I'd like to start with memory stats. This gives a high-level overview of where memory is allocated, how much has been allocated and freed per process. And that information is all available on the login node. So I like starting with that in that it's a good high-level view, and it's also very efficient even when you're running at larger scale. Then the next step is to go to memory usage, which goes out to the compute nodes, gathers detailed information about which processes are actually using memory, and it'll break it down here as you see in the legend, and you can drill down into that. So kind of a whirlwind on that. It takes a while to go into that, so we can do that in breakout if you're interested. There's some videos, pretty straightforward, really. So I'm going to move on to, so we talked about performance reports. I'm not going to say too much right here about that. It's a one-page report. I am going to move on to map of, kind of give a summary of some output for that. But are there any questions on DDT at this point? Yes?
So how about following across forks?
So you can debug into a fork. Is that what you mean, just being able to trace into it? So yeah, so there's a couple methods of set a breakpoint in the forked code. The more, I would say, effective is if you can set a breakpoint at the point that the fork is going to occur and then step into it is the most productive. Now I'll caveat that with it often gets complicated because knowing the context that you're looking at, that's why I like the approach of set a breakpoint at the point you're going to step into it, because then you manually see the context of it saved, but that all works. Once again, that's an area is like kind of looking at it. As I said at the beginning, we're very focused on traditional HPC, SPMD codes, for which I'd say we don't see that often. But it does work, and obviously as the world is changing, we're seeing more non-HPC codes and trying to address them.
So, I see this in codes at Livermore where they call system out of an HPC application, and stuff goes wrong on the other side.
Yeah.
So, yeah.
It's complicated in any scenario, but I've worked with customers and I've seen customers have success stories for it. It definitely is another. That's really my best advice is try to step at the point of the fork, see the context, and step into the fork. So the workflow with map is inherently offline, so to speak. You can run it interactively. I recommend essentially never doing that, unless you're just playing around with very short runs. Once again, our profiler is designed for rather long runs, where your code runs for many, many minutes, if not hours. That's the sweet spot for gathering data. And in that mode, the workflow is you go into your batch file, prefix the existing app run, MPI run with map dash profile. It will run and generate an output file, then go back to the client on your desktop, connect to your cluster, and at that point you'll be browsing the file system of the cluster and bring up the result data. Now, just 2 pennies on the sampling process. In general, the overhead is very low, just a few %, but depending on the size of your run, it takes some time at the end of the run to aggregate the data. So if your run typically takes an hour, start out giving a good liberal amount until you get some sense of how much extra time the map takes to aggregate the data for your run. So I'm just going to bring up a file that I have previously generated in that kind of workflow and talk a little bit about the user interface. Okay, so at the top we have various charts. We call this the activity diagram. The top chart shows time spent in single thread compute in dark green, I/O is in orange, MPI is in blue, GPUs would be in purple, OpenMP would be in gray. There's about 8 high-level metrics. The point being is it's very easy at a glance to get a sense of what the program is doing. So with this program, we can tell right away there's a little teeny bit of I/O, so we can bypass that milestone on the performance roadmap. We can see there's a lot of blue, and so that'd be kind of milestone 2 or 3. That might be a matter of interest. There's no multi-threading. That might be a concern once we get down that far in the performance roadmap. So at a glance, we can see a lot about kind of the demographic of the program. Then the charts below that are the various metrics we gather data on. Within the plot, it shows the minimum, maximum, and mean as a solid line. The shading around the mean is kind of a variance across all the processes. So for my application, it had 8 processes, but even at thousands of processes, the shape overall would be the same, but the scalability of being able to see variance in the shading would be the same. And you can get the instantaneous values of that by hovering over the chart. So I can see at about 3 seconds in, floating point was ranging from 0% on rank 3 to 90% on rank 7, with a mean 15 a standard deviation. So standard deviation is kind of a red flag here. That's pretty high standard deviation for this kind of run. So at some point, once we've ironed out earlier milestones on the performance roadmap, that might be something that we'd get to. The center pane source code view, somewhat similar to DDT, except to the left, we have a small representation of the activity diagram, and we can hover over that and get some details. So for example, in this case, we can see that that call to imbalance on line 10 was about 50%, quite a bit in MPI, quite a bit in single-thread compute. Then to the bottom, some kind of bottom-up views of like gprof style, where you can see by function, by children of function. But I really recommend focusing on the charts first, and let me just kind of highlight how that works. So we saw that there's a lot of blue. So that's a pretty early milestone on the performance roadmap. So let's explicitly add in MPI call duration. And we can really highlight the problem by if we hover over it, so the kind of the first sawtooth here, we see that the MPI is ranging from 0 seconds on rank 7 to 3.4 seconds on rank 0. So that's enormous. That means there is a process sitting for 3.4 seconds doing no work. So that's definitely a problem. So the workflow in map of like trying to isolate that is highlight the section of the chart with the problem, and it'll update the interface to show the time spent within the selected window. And then most importantly, in the bottom, it will only show data for the area that I've selected. So at this point, I can see 100% of my selected window is within this imbalance function. And then the way to isolate that is we collapse all the code blocks, and then block by block, drill down to see where that is occurring. So at this point, we've narrowed it down to essentially a couple lines. There's this MPI reduction and this computation line. So at this point, it's kind of a fun exercise of using your debugger to help you understand this. So like in a tutorial situation, I'll often like say, half the class, go right to the debugger, step through the debugger, studying the code, using the debugger as a study tool, if you will, and see if you can find the problem, or just study the code directly. And even with this rather trivial code, folks that use the debugger to understand the code overwhelmingly win the contest. But the punchline is for this one, we would see that we're iterating over the rank number and we're not distributing that computation load across the available processes. So that's kind of a whirlwind of map, but whether it's MPI, IO, OpenMP, whatever metrics, the workflow is look for problems in the chart, as we did with MPI, highlight that section of the chart, then collapse the code blocks, go down, step down block by block. It's usually 3, 4, maybe 5 in an HPC code to isolate the inner blocks where the time is being spent, and then try to step up from there. Okay, so that was kind of whirlwind map. Like I said, we can go over more in breakouts if you want to. We can like bring up your own codes. Like I said, I really encourage you. There's a lot of expertise here today for performance and debugging, and you've got a couple breakout sections to take advantage of. Well, all of these experts are here. But that's it. I think we have a couple minutes for questions. Great. Well, thank you. Yes?
How do I get a license cheaply?
So most institutions have it. Which institution are you with?
The institution does, but my professor has a workstation that I also want to use, and I want the license for that.
Come see me, and I can connect you with sales. I think you can actually buy it online. And if you're a student, there might even be something a little better to be had than what our online price is. So connect with me, and I'll connect you with sales that can hopefully get you set up with something.
Okay, so thank you, Beau.
Yes, thank you.